Okay, we are going to talk about the systems of linear equation, which lies at the heart of linear algebra. Let me start with what is a linear equation. The linear equation with the variable x1 through the xn can be written as following. The constant a1 times variable x1 plus constant a2 times variable x2 and constant an times variable xn is equal to v, something like that. So linear equation is just combination of linear terms with a variable x1, x2, or xn, something like that. Okay, let me see the example. Let me show some example. So let's say there is 3x1 plus 2x2 equals 6. This is the example of linear equation. Maybe you are more familiar with this notation like 3x1 plus 2y equals 0. But in this course, we will use this terminology because we can deal with so many variable like the x1, x2, x6, x16, something like that. So this notation is much preferred than this one. So this is the examples of linear equation. So what is not a linear equation? For example, let's think about 3x1 square plus x2 equals 1. Or there is the x1 plus 2x2 is equal to something like that. So in this case, it's not a linear equation. Why? Because this term, this is not a first order variable x1, and this is not a first order of x1, so it's not a linear equation. Another example is like this: x1 times x2 equals 0. This is also not a linear equation because this x1 and x2 have the first order, and then this term will have the order of 2, so it's not a linear equation anymore. So in this course, we are just dealing with this kind of linear equation. More generally, it can be represented like this. So this is a linear equation. So how can we plot this linear equation? What is the graph of this equation? When you draw the linear equation, we are talking about lines. Okay, let me see. Let me show you something. So, okay, we have a linear equation x1 minus 2 times x2 is equal to negative 1. So how can I draw this? So first of all, there is x1 and x2. When x1 is equal to 0, when x equal to 0, so x2 is going to be the 1 over 2, right? So it should be here, 0, 0, comma 1 over 2, something like that. And when x2 is equal, this is x1 is equal to 0, and x2 is equal to 0, and x1 is going to be equal to negative 1. Okay, so when x2 is equal to 0, x1 is negative 1, so negative 1, 0, something like that. So this is just the two points that satisfy this linear equation. But if we find a more point that satisfies this linear equation, we can draw the line like this. Okay, so this is the way to plot the linear equation. So this is just a two variable case. what about the 3 variable case, like the x1, x2, x3, something like that? So can you imagine? So in this case, we should plot this equation in a 3D space. I mean 3D-dimensional space. So in this case, if we have just a 2 variable, it can be represented in the 2D space. But in this case, we need a 3D space. Okay, let's do that. So because we have a 3 variable, x1, x2, x3, something like that. So how can I draw this? So when we x1 is equal to 0 and x2 is equal to 0, then x3 is going to be equal to what? 6. Okay, so when x0 is equal to x1 is equal to 0, x2 is equal to 0, x3 should be 6, like this. Okay, when x is equal to 0 and x3 is equal to 0, x2 is going to be what? 6. Okay, so 0, 0, 0, 6, 0. Okay, so 0, 6, 0 here. One more point. So when x2 is equal to 0 and x3 equal to 0, x1 should be what? 3, right? So this point will be here. 3, 0, 0, something like that. And there will be another possible point in here, like this. But in this case, in the 3 variable case, this point that satisfies this linear equation can lies on this subspace and this surface, like this. Okay, so comparing to the 2 variable case, the 3D variable case can generate the one single surface like this. Okay, so this is a linear equation. Okay, then what is the systems of linear equation? It's just a collection of the one or more linear equation. Let's see the example. So this was just the one single linear equation, but in the systems of linear equation, we have a more linear equation like this. So this is called the system of linear equation. So with this information, we can find the solution for x1 and x2. That satisfy these two equations. So what's the meaning of the solution for the linear system? So the solution is to make each equation true statement when the values are substituted for the variable. Okay? Then how can you solve this? We will already learn in the middle or high school. In this course, we are going to learn how to solve this in a systemical way in the linear algebra world. Anyway, in this case, x1 will be the 3, and x2 will be the 2. So this will be the solution of this linear equation, because it makes each equation a true statement when the values are substituted for the variable, right? So this is the solution of this linear systems of linear equation. Then what is the solution set? It's just set of all possible solution. So this is the system of linear equation. the system of linear equation is also called the linear system. So in this course, we can use terminology of the system of linear equation or just linear system. Okay. So how can I solve this linear equation? For example, we have a two linear equation with a two variable like this. So there is the x1 and x2, and with the equation 1 and equation 2, two linear equation. So how to solve this linear system? The easiest way is to find the intersection of the two lines that represent each equation. So how can you draw this? Do you remember this? So first of all, this is x1 and x2 like that. So x1, when x1 is equal to 0, x2 should be 1/2, and x2 is equal to 0, the x1 is equal to -1. No. -1 to 0, something like that. So this first equation draw this line, and another equation is from this. So when x1 is equal to 0, the x2 should be 1, and x2 is equal to 0, the x1 should be -3, something like that. Okay, so then represent another line here. So this is another line. So the solution of this linear system will be the intersection of these two lines here. It will be the x1 is equal to 3, x2 is equal to 2, something like that. Or we can just represent 3, 2. Okay, so this is just the solution of this linear system. Okay, it's very easy, right? But let's think about the more difficult case. I mean, more high dimensional solution. Okay, if we think about these three variable case, can you solve the solution like using this drawing, something like this? No, we need a more systemic way to solve the more higher dimensional problem. So in this lecture, we will learn how to do this. Okay. Before that, we should think about the possibility, the solution possibility of the linear equation. So when we have a systems of linear equation, there are several possibilities about solution. So first of all, if we have a two equation like this, like this, like this, we can have a line that looks like how can I do this? Okay, let's draw it again. Right, like this. Okay, so first of all, if these two lines meet at some point here, we have x1 is going to be the some number, x2 is going to be some number like this. We have an intersection of the line, and we get a one exact solution here. So this is called the one solution case. Actually, this line is not exactly mapping to this function, this equation. So try to draw the equation exactly yourself. Okay. So yeah, So another possibility is that we have an infinitely many solution. I'm going to do line 1 in like here, like this, and draw the another line like this. Okay? For example, in this case, we have exactly same line, so they are equal to each other at every point. So every point. So they are equal to each other at every point and every possible point. So there will be the infinitely many solution. Okay, so this is the another possibility. And there is one more possibility. If these two lines are parallel like this, they don't have any solution. In this case, two lines will never meet. So like this. So two lines will never meet. So there will be no solution in this case. So there are three different possibilities of the solutions of linear system. Interestingly, there are only possibility we can have for the solution. Why? Because we are dealing with a straight line like this. So when we're dealing with a straight line, this line is never going to meet up over 2 or 3 points like this. For example, if we draw the two lines like this, okay, let's draw again. Like this, there are only 3 possibilities, like the one solution, infinitely many solution, no solution case. But these two lines meet 2 or 3 or 4 point because we are dealing with a linear equation. But if the graph looks like this, for instance, a parabola case, there would be another possibility like this one. But in the linear equation and linear system, we don't deal with this case. So to summarize, there is only 3 possible solution cases. Okay, let's move on to the consistency. A system of linear equation is consistent if there is at least one solution. Otherwise, it's going to be inconsistent. Okay, so in the first example here, okay, let's see. Okay, so in the first example here, this equation make the line like this. Is it correct, right? And this equation make the line like this. Okay, so as you can see here, these two lines doesn't meet forever. So like this, so there will be the no solution. So in this case, it is called the inconsistent case. Inconsistent case mean these lines will never meet each other, so there is no solution that satisfies this linear equation, like that. So this is an inconsistent case. Another case is like this. So this first line looks like, okay, let's see the 0.5, and when x2 is equal to 0, the x1 should be 5 over 2, so 5 over 2, like that. So 5 over 2, 0, something this. Yeah, this is the line for this equation. And another line it looks like how can we trace it? Looks like this, something like this. Please check this is correct or not. So anyway, there is a solution, right? There is the exact one solution. So in this case, it is called the consistent case. So we can say that this linear equation or linear system is consistent, right? So this is the consistent case. So this is the inconsistent case. Okay. So there are terminology we are going to be using consistent and inconsistent. Okay. The last concept and last terminology is the equivalent. What is the equivalent? Two linear systems called the equivalent if they have the exact same solution set. Okay. What does that mean? What does that mean? So, okay. Okay, let's think about these two linear system case. This is a linear system 1, and this is a linear system 2. Okay, let's use a different color. Okay, linear system 2. Okay. Okay. So we can draw this linear system as we discussed previously. So what is that? So x1 is equal to 0, the x2 should be 1, something like this. And when x2 is equal to 0, x1 should be 1 over 2. So 1 over 2, 0, something like that. So this is the first line. The second line is the x1 is equal to 0, x2 is equal to -5 here, and x2 is equal to 0, x1 should be 5 over 4. Okay, so 5 over 4. 5 over 4, 0. So these two lines represent this linear equation. Yeah. So what is solution of this first linear equation? What is that? What is that? x1 is equal to 1, x2 is equal to -1. Or we can represent like -1, -1, something like this. So this is the solution of this linear system. There is another linear system, look like this. So we can also draw this linear system like when x1 is equal to 0, x2 should be -2, something like this. And when x2 is equal to 0, x1 should be 2. Where is that? This one is 2, something like that. Oh no. Okay. So this is the first one line. And another line is when x1 is equal to 0, x2 should be -5 over 3. Okay, -5 over 3 here. So x1 is equal to 0, x2 is -5 over 3 here, and x2 is equal to 0 to x1 should be 5 over 2. So should be 5 over 2, something like that. So this is okay. This is lines looks like this. Okay, so in this case, these 4 lines meet at a single point. So it means that these two linear systems have a same solution set. Then in this case, it is called these two linear systems are equivalent. Okay, so we can say that these two linear systems equivalent. Okay, so in this case, this is equivalent case. Then what about this? When this coefficient is 2 and this coefficient of 4, in this case, this line will be the exactly same to this one. It is same to this one. Yeah. So this linear system can have infinitely many solutions. What about this case? This is not equivalent. Why? Because this linear system only have one single solution, but this linear system have the infinitely many solutions here. So these two linear systems don't have the same solution set, so it's not the equivalent anymore. Okay, so this is a concept of the equivalent. Okay, here's where linear algebra and this equation get a little bit nicer, because we deal with so many equation and variable, and we know how to use them, but we don't like to write the x1 and x2, x3, something like that, every variable, every time. It's a lot of work. So instead, we can record the linear system into the matrix. Okay? So what is a matrix? Okay, let's see the example. Here is the linear system with the 3 equation and 3 variable. Okay, so we can just represent these linear systems as a matrix. Okay, so let's say actually there was the coefficient 1, and there was the coefficient 0 times x3, and there is the coefficient 0 with x2, right? So then what is the coefficient matrix? Just to write each coefficient here, and so in here the coefficient 2 from this one, and coefficient 0 from this one. Okay, so like this we can write the coefficient matrix like 1, 2, 0, 3, 0, -4, 2, -1, 1, something like that. So this is called the coefficient matrix. So with this coefficient matrix, we can represent the complicate the linear system in a very efficient form or efficient notation like this. Okay. Then what about the augmented matrix? Okay. When we think about the linear system like this, we will the coefficient information like this was containing here, but what about this? So in augmented matrix, we can duplicate these values right of the coefficient matrix here. So yeah, in this case, it should be 5, 2, 6, something like that. So augmented matrix of system consists of the coefficient matrix with an added column containing the constant from the right hand side in the equation. Okay, this is called the augmented matrix. So from now on, when we talk about the matrix, I will always talk about the augmented matrix. Okay, so when we see the one augmented matrix, we need to think about how can we reverse this linear equation from the augmented matrix. Okay, so we need practice. Okay, so we have a matrix and we have to give it size and we have to be consistent with our naming. So when I say, okay, let's see this part. So when I say this matrix is the 3 by 2, we need to be able to think about in your hand 3 by 4 means there is 3 rows and 3 columns and come up with the size of the shape of it immediately. So what is the size of the matrix? So the size of the matrix is n by n like this and like this. So actually we can represent the size of matrix as rows and column. What is row? The row means just the entry of the values like this, and column is just like the entry of values like this. So this is the meaning of the rows and columns. So okay, let me see another example. Yeah, there is no example here. Yeah, I can draw that. So there is a matrix like the 1, 2, 3, 4, 6, 7, -1, 1, 1, something like that. What is the size of this matrix? What is the size of matrix? Because there are 1, 2, 3 row and there is 3 columns like this. So the size of this matrix should be 3 by 3. Okay, so this is the size of the matrix. Actually, the terminology of the rows and columns is sometimes very confusing. So I searched the meaning of columns. Not a linear algebra meaning, but just real meaning. It was just like this in Google. So the column means like, how can I see? Like this, as you can see. So when we think about the column, so we can imagine what is column and what is row. Okay, so if you remember this page, I'm sure you never forget about what is column and what is row. Okay, let's see one more thing. So in this lecture, we are just talking about the matrix, but there are another terminology that represent the array of values. As we discussed, the matrix was a 2D array of numbers. 2D array of numbers. What about one-dimensional array of the numbers? It is called the vector. So in this case, like this. So as you can see here, the vector consists of some values like this, or with a one-dimensional shape. So it can be represented like this. In this case, there is 64 values here, and matrix case, it can be represented like this because there are 8 rows and 8 columns like this. So this is a matrix form. What about the 3D-dimensional case? It is called the tensor. It's called the tensor. So as you can see here, there are one matrix here, and there's one more matrix here, here, and here. Okay, so there are four stacked matrix, so the size of the tensor would be represented like 4 by 4 by 4. Okay, so this is a tensor. So why did it is important? Okay, let's see the example. I'm not sure how many of you are familiar with the deep learning, but I guess most of you heard about deep learning or called the AlphaGo, which is an algorithm to solve the Go game made by Google. So it was a revolutionary success of deep learning, and nowadays we are living in deep learning world. So many real applications like the social media, transportation, finance service, healthcare, something like that have benefit of deep learning and artificial intelligence. So I'm not sure when I'm sure when you graduate the university you must know the deep learning or artificial intelligence to get your further position. Okay. So anyway, so deep learning, the deep learning architecture looks like this and this. This is called the VGG network, and this is called the ledger network. You don't need to remember this, but just see. And when we see the architecture in detail, the architecture looks like this. The input is consisting of the some tensor notation, and the core of this deep neural network actually is just called the convolutional activation, something like that. But you don't need to remember this. But anyway, so in deep neural network, most component is consisting of the tensor representation like this. As you can see another example, there is consisting of the tensor representation like 3 by 3 by 64 tensor like this. So the linear algebra is just starting point and fundamental subject to be an expert of the artificial intelligence. So that's why we are here now. Okay, so let's go back to the lecture. Okay, we have a linear system. Then how can we solve this in a systemical way? The basic strategy is to find the solution set by replacing one system with an equivalent system that is easier to solve. What does that mean? Yeah, let's see the example. Here's a two linear system 1 and linear system 2. Yeah, here's the two linear system. If you remember correctly, where was that? Yeah, here. It has a solution in 1, -1, right? So yeah, the solution of this linear system is x1 is equal to 1 and x2 is equal to -1, like this. And what about this? What about the solution of this linear system? It is like x1 is equal to 1, x2 is equal to -1. Why? Because there is a 0, this term is have no meaning, and we can just say that the x1 is equal to 1, x2 is equal to -1. Okay, so if you remember previous page, these two system is call the what? Equivalent system, right? Because they have the exact same solution set. Okay, so what we want to do is if we have the linear system that we need to solve, we can, if we can transform or convert this linear system to another linear system like this that is easier to solve, we can solve the original linear system more efficiently, right? So in other words, the linear system is much easier to solve because it just gives us the solution directly. So from now on, we will learn how to convert this original system to the simpler system like this. Okay. Here is the example. Solve the given system of allocation. This is the problem. So actually, we already learned this in the middle school, right? There was many possible ways to solve this. There was a very popular solvable called in Korea. What is that? It's called the 가감법. Yeah. So how can we do this? Yeah, let's see the example. In this solution, the elimination procedure is shown with and without matrix notation. The results are placed side by side for comparison. So after this equation, after with this example, we will deal with the matrix form. But in this example, we just to deal with this equation form, and we can compare which one is the more efficient and effective to solve the problem. Okay, so let's start. So first of all, we have 3 equations and 3 variables, right? Yeah. So what is the augmented matrix of this linear system? Like this, right? So this is the augmented matrix of this linear system. So these coefficient values are from here, right? So because there is the 0 here, so we can write the 0, 2, -8, 8, -4, 5, 9, -9, right? So this is augmented matrix. What is the size of this augmented matrix? What is that? 3 by 4, right? Because there is 3 rows and 3 columns, right? So this is an augmented matrix. But in this example, we're just dealing with these linear equations. Okay, so what do you want to do? So first of all, we want to remove this variable x1. Okay, so how to do that? First of all, keep the x1 in the equation number 1, this one, and eliminate it from the other equation. What does that mean? So first of all, we have x1 negative minus 2x2 plus x3 is equal to 0. And first of all, we multiply first equation by 4, like this, the 4x1 negative minus 8x2 plus 4x3 is going to be equal 0, something like that. And then we can just add these two equations like this, and it will be removed, and this coefficient will be the -3 because -a plus 5 is equal to -3, and this it will be the 13, and it will be the -9, right? So this is the first stage, and after this stage we can get the equations looks like this. These two equations are not changed, but we convert this last equation looks like this. Okay, how can we represent this linear equation in a augmented matrix form? So in this case, it is looks like 1, -2, 1, 0, 0, 2, -8, 8, 0, -3, 13, -9, right? So comparing to this previous equation, this original augmented matrix, okay, let's remove it here. What's the difference between the original augmented matrix and another augmented matrix? We removed this part, right? We removed this x1 variable like this. So what does that mean? So in this case, we just have a single variable in the first column. So we can find the solution for variable x1. So what is the next? So from this part, I want to remove these values using this equation. Okay, so how can we do this? First of all, we can multiply the equation 2 by 1/2 in order to obtain the 1 as a coefficient of x2 like this. So okay, let's do this. So it was the original equation here, but we can just multiply 1/2, and we can get the new equation like this, and this whole equation can be transformed or converted to the augmented matrix like this. Then we can use this number to remove this number. How can we do this? We can just multiply this equation 2 by what? 3, right? So x2 negative minus 4x3 is equal to 4. We just multiply by 3. It will be the 3x2 minus 12x3 is equal to 12, right? And the original one was the -3x2 plus 30x3 is equal to -9, right? So after that, how can we get the solution of x3? We can just add these two equations, then it will be the 0 times x2 plus 1 times x3, so it's just x3, right? And 12 12 minus 9 will be 3. Okay, so finally x3 is going to be equal 3. Okay, so if we write this equation again, so this equation is converted, looks like this, comparing to the original equation here. This equation looks more simpler, right? So we can also represent this equation as an augmented matrix form like this. Okay. Now we want to eliminate the, where is that? Yeah, this part, right? If we eliminate whole of this part, we can just get a solution about x1, x2, x3. So we want to eliminate the negative x2 first, right? But if there is a more efficient way, we want to do like this. Okay, so what do you do first? So rather than eliminate the negative 2x2, we start from here. I mean, if we can eliminate this part first, and we can finally eliminate this part, it will be the more efficient. Okay, how can we do that? So first of all, we can just multiply this equation 3 by 4. So it will be like this. 4x3 is equal to 12. And there was the original equation 2, x2 minus 4 times x3 is equal to 4. And if we just add these two equations, we can get x2 is equal to 16, right? Then what do we do next? Then we already know the negative x3 is equal to negative 3 from this equation. x3 equals 3 times negative 1, right? And if we add this, this is the first equation. If we just add these two equations, we can get x1 times x1 minus 2 times x2 is equal to negative 3. Okay? This will be the new equation 2, right? So combining the result of these two operations, we can get a more easier notation like this, right? Because these equations are from here, these equations are from here, right? And these values are also represented in an augmented matrix form like this, right? So where are we here? Comparing to the original, comparing to the original linear system, we make a much easier form from the original equation. Still, we have these those equations, those linear systems have the same solution set. It means that they are equivalent, right? So it means that if we find the solution from this linear system, it will be the solution of the original linear system, right? So what should we next? We have to remove this part, right? How can we do that? Just add this value here, and x1 is x1 minus 2 times 16 is equal to negative 3, and then x1 will be what? Will be what? 32 minus 3 and 29, right? So from here, finally, we can make this first equation looks like this. So finally, we make the three equation looks like this, and this is converted to the augmented matrix looks like this. And what you can learn, the solution of this original linear system is x1 is equal to 29, x2 is equal to 16, and x3 is equal to 3, right? So this will be the solution of this linear equation. Okay, so the only solution of this original system is 29, 16, 3, right? How can you verify this? Just substitute this value to the original system. What was that? Here, okay? Okay, so yeah. What was that? So original system was x1 minus 2 times x2 plus x3 is equal to 0. 2x2 minus 8x3 is equal to 8, and negative 4 times x1 plus 5x2 plus 9x3 equals negative 9, right? This was original system, and we can substitute these values here, right? Then the 29 minus 2 times 16 plus 3 is equal to 0, right? And 2 times 16 minus 8 times 3 is equal to 8, the same, right? Same to the right hand side. And minus 4 times 29 plus 5 times 16 plus 9 times 3 is going to be equal to negative 9, so it is same, right? So you can do this by your hand. Anyway, this lizard agree with the right hand side of the original system, so we can say that this is the solution of this linear system. Okay, so we can represent this solution in the three-dimensional space. Okay, do you remember how can we draw this three-dimensional three-variable case? Okay, so this is the original linear system. So we can say that what's that? x1, x2, x3, something like that. Then each equation can be represented as a surface like this, and the solution is the intersection of this linear plane. So original solution. Let's see. Yeah. So if we can draw this surface, we can find the solution like this, right? So each of original equation determine the plane in 3D domain, like that. So this is a solution of this linear system. Okay. Okay. So from now on, okay, let's go back to what we have done. So to solve this complicating equation, we convert this equation to the more simpler simpler cases, and finally get the result, right? What about the matrix? What about in the matrix form? Let's focus on the matrix form. Here, comparing to the equation form, the matrix form was much efficient, right? Like this, like this, like this, like this. So if there is a matrix operation to do this complicated procedure using the matrix operation, we can solve the linear system more efficiently and more systemically, right? So what is that? This will be the elementary law operation. Then next time we will learn what is the elementary law operation and how can we solve this linear system in a matrix domain. Okay, so this is